Okay, so in the 2 by 2 case, you can definitely do it by exhaustion. But what about as we get up to a 2000 by 2000 board? So in a situation like that, we're going to have trouble. Right. And then, just one second, Adam, is it recording over here on Globe right now? Okay. Okay. So one idea is to try to use induction. And again, we can easily do the 1 by 1, 2 by 2, 3 by 3. So now for the 4 by, let's say we're trying to do an induction on the 3 by 3 case. So we know for the 1 by 1 and 2 by 2 it's fine. So for the 3 by 3, we can say if we have one square in here, uh-oh. Are you still there, guys?
Yes.
Okay. It says detected connectivity problems reconnecting.
Yes, you seem to not be the presenter anymore. No, there you are.
Okay. Interesting. No one else is supposed to have the power to take me off presenter. I think my students would love to know how you did that. Okay, so we could try to do it by induction. So if we have one piece in here, we know we can only infect one more. I mean, we can't infect any more. And then we can worry about over here. To me, it just seems like it's going to be a painful induction to try to do. So the question is there a better way to approach this? And that's what I want to talk about today. That's the main point. It's called a monovariant. So how many of you have ever heard of a monovariant? Okay, how many of you have ever heard of an invariant?
Yeah.
Okay, so anybody want to say what an invariant quantity is?
Just something that doesn't change.
Good, an invariant quantity is something that doesn't change. So for instance, if I take a triangle and I translate the triangle, or if I rotate the triangle, the area is invariant under that transformation. Invariant quantities are wonderful in mathematics. When you're trying to study spaces, you might say, well, if these two spaces, maybe there's a nice continuous transformation between them, what properties are preserved? These are things you love to look for. A monovariant is not quite as good as an invariant, but it's often good enough. So a monovariant only moves in one direction. So as time passes, your quantity either stays the same or goes down. Or it stays the same and goes up, but it never switches between going up, down, up, down. So what we're going to look at over here is the perimeter of the infection. So imagine right now I have two cells that are infected and the cell between them is not infected. And we want to look and see what happens to the perimeter of the infection. The main thing is over here, you can hopefully see there's two internal walls of this cell that's not infected that are going to become infected. And those two walls are going to make up for the two walls over here in the infection. So when we look at what's going on, if you look at the perimeter, these are now internal walls. They don't count towards the perimeter of the infection. This wall and this wall might count. Why might they not count?
If there are infected things above or below.
Yeah, so if there's something infected above and below, I don't want to go into all those cases. So I don't know necessarily what's going on above and below. So worst case scenario, if I have a cell that has neighbors on the left and right and it gets infected, the perimeter doesn't change. If I had cells above and below as well, then the perimeter would actually go down. So there's not that many possible cases to look at. I can have two horizontal, I could have two vertical. I could have 3 out of 4, or I could have 4 out of 4. That's not that many cases. And in all of those cases, you see that the perimeter of the infection does not go down. So how does this allow us to elegantly solve the problem now? Okay. Yes?
If we have n-1 infections initially, we know that like if we take, I don't know, sort of the leftmost,
Are you guys able to hear her as she speaks?
I could hear that.
Okay.
The
Why
top.
don't you come next to the computer?
So if we have
Why don't you sit down and let's just make it.
It's kind of awkward.
Yeah, the technology is not working as well. So
if we have n-1 infections initially, and if we take the top left red square of these n-1 squares and the top left and the bottom right square, we know that if they're not wait, let's just do left and right. So if we take the leftmost square and the rightmost square, we know that they are they're n-1 apart at most.
I think you're making it too complicated.
Oh, okay.
So
Well, I mean,
you gotta come down.
or
Like,
louder.
I mean, the idea, if you start with n-1 squares and you look at the maximum perimeter you can have with n-1 squares, then because you know what if everyone were to be infected, you know what the perimeter would have to be of the infected area. If the maximum perimeter for n-1 squares is less than the perimeter of the entire square, then you wouldn't be able to infect it.
So I mean, if you try to do the left-right argument, you might be able to make that work, but it's going to be a lot more convoluted. So each square, its perimeter is 4. So if there's no overlap between the n-1 squares, the maximum perimeter we can get is 4n-4. But the perimeter of the whole square is 4n. So since the perimeter never increases as the infection progresses, the maximum perimeter we can get is 4n-4. So we can conclude there's at least one person that's not infected. Okay, so imagine now we have a 4x4 square, and we infect 3 cells. Because of this monovariant argument, we now know that there has to be at least one square that's not infected. Do we all agree on this?
Yes.
Yeah.
So there's at least a safe place for people to be. Could there be only one square that's safe?
No.
Okay, why not?
It would just immediately get affected. By
Yeah, it would be immediately infected. So if you have one square, let's say this square over here is not infected, well, it's got 2 neighbors that will infect it. So if it's a corner, it gets infected. If it's an edge, it gets infected. If it's a middle, it really gets infected. So now we know there's at least 2 cells. So a result actually improves itself very quickly. What about 3 cells? Does there have to be an entire row or column? I will leave that for you guys to ponder as extra credit. We know that the monovariant argument initially only gives there must be one safe. We immediately get that there must be 2. You could probably quickly get that there must be at least 3. Can you push it and get that there must be a whole row or column of safety? Okay, this was just so we could do some drawings, but I'm going to skip the drawings with a tech. So what I want to end with is, I want to end with something related to my research. And so one of the reasons we were starting at 8:20 is this way we had enough time so it would be done easily by 9 o'clock. So a monovariant is a quantity that only increases or decreases as we move. And so the question is, where else can we find monovariants? This is not one of the more common problem-solving techniques that people have seen. It takes a little bit longer to be comfortable with this. There's a lot of great stories about the Nobel laureate Richard Feynman. And one of my favorites is he had this reputation of being able to solve integrals that no one else could. And he would solve them quickly. And the reason he could solve them so quickly is the people who gave him integrals to solve weren't idiots. These are good students at MIT or Princeton. And so what Feynman said is, they've probably tried all the standard tricks, and if the standard tricks worked, they would have solved it. So if they're bringing it to me, the standard stuff can't work, let me try something new. Most people don't know about differentiating under the integral sign. And so he would try that first, and he'd solve it. And they'd be amazed. So this is a new thing to add to your repertoire. So I want to talk about one of my favorite theorems, Zeckendorf's theorems. So for this, I'm defining the Fibonacci numbers as 1, 2, 3, 5, 8. So each one is the sum of the previous 2. it's very important that we start with just 1, 1 and not 1, 1 or not 0, 1. And the reason is this beautiful result that every positive integer can be written uniquely as a sum of non-adjacent Fibonacci numbers. So for example, 82, I have no idea why I chose 82, is 55 plus 21 plus 5 plus 1. The standard way you prove this is the greedy algorithm. You take your number 82 and you subtract the largest Fibonacci number you could. So the largest Fibonacci number less than or equal to 82 is 55. 82 minus 55 is 27. I then subtract the largest Fibonacci number less than or equal to 27. And if they had been adjacent Fibonacci numbers, say I could have subtracted 55 and whatever was adjacent to them, why would that be a contradiction?
You would just use itself as a...
Yeah, I would have been, so the suggestion was that I could have just used their sum. So if I could subtract 55 and if I could subtract the one next to them, I should have subtracted the sum of 55 and the one next to it. I'm a moron. So the greedy algorithm will tell you that there is a decomposition. It doesn't tell you that it's unique. You have to do just a little bit of work to prove that. All right, everybody comfortable with Zeckendorf's theorem? Okay. So here's the following. There are many ways of writing a number as a sum of Fibonacci numbers. Can somebody give me a way of writing 16 as a sum of Fibonacci numbers? Okay, so one suggestion was 16 ones. So thank you. That is the worst possible way of doing it. You use as many summons as possible. Can somebody give me a better decomposition than 1, 1, 1, 1, 1, 1, 1, 1, 1?
3 and 13.
3 and 13. Can somebody, so that only has 2 summons. That's much better than the 16 ones. Can anybody give me another decomposition?
8 and
8 and 8. So this is one data point, but that's more than enough to conjecture since we had technical issues and have to go fast today. So the Zeckendorf decomposition, it seems like no other decomposition has fewer summons. You may have another decomposition that has the same number of summons, but nothing seems to have fewer. Now this is just one data point, that's not really good, but what kind of rules can we do? Well, we can split a double. If I have like 2 8s, I can represent 8 as 13 plus 5. And so I use 2fn is fn plus fn plus fn minus 1, and then fn I'm sorry, this should be fn plus fn minus 1 plus fn minus 2. And this should be fn plus 1 plus fn minus 2. So I'll have to fix the size there. This should be in minus 2. Let me see if I can quickly fix this. N minus 2. Okay. So, and if I combine adjacents, fn plus fn minus 1 is fn plus 1. So I have these nice rules to combine. What I want you to do is think about what kind of monovariant can you attach to a decomposition. So you have a bunch of summons. Find a monovariant. And as you keep applying these rules, you will eventually end in the Zeckendorf decomposition. Sometimes you have fewer summons, sometimes you have more summons. So can you use this to prove that among all decompositions, the Zeckendorf decomposition has the fewest summons? So I first noticed this many years ago when I was giving a talk at Hampshire College. I then wrote it up a year later with some colleagues, and then last summer some of my students and I really pushed this far to more general occurrences, and wrote a really nice research paper along these lines of applying this monovariant argument. So this is a really good thing to think about. All right, so I will fix the typo. Does anybody have any questions? All right, well, it was nice talking to you guys remotely. I will send you some emails to get some feedback as to what's going on. We will work on the wireless, but what my students told me is starting last night, there seems to have been a wireless issue on campus. And so this is what, problem solving, this is not necessarily the problem I wanted to solve, but this is why when I came down today, in addition to the Surface, I have a computer with a alternative way of projecting the slides, and I had looked at the equipment in this room to figure out where are the cables so I could quickly unplug them if needed. So, have a great day, guys.
You too.
Okay, bye-bye. And then Adam, do I hit the record button over here to stop? Oh wait, this says to start recording. Was it not recording?
That's fine. That's not really important. Well,
Alright.
I think Adam will have.
Alright, well here, it's recording right now in the beginning. Alright, so
You just close that one.
what I'm going to do is, just because we missed the first few minutes of the recording kind of,
Or no, we're back.
well, here.
No, you're switching the tab.
Oh,
You see the tab?
which tab?
Top right. Top right.
Top right.
Tab. You switch tabs.
Oh, I switched tabs. Oh, okay.
And then you close it by hitting the. You see it?
Okay, so what I'm going to do is, because we missed the first few minutes, I'm going to just quickly run through the first few minutes because it's recording on the iPad now. Alright.
Yeah.
So if you've already joined us, you guys can sign off and have a great rest of the day.
Yeah, right.
Okay? Okay. Okay. So we were talking about zombie infections, and so the idea of zombie infections is if you share a wall with 2 or more infected people, you become infected. The zombie rules we are using is that once you are infected, you are always infected. You can never kill a zombie, they're already dead. Diagonal sharing does not count. So in this configuration, this cell here and this cell here would both be infected because they share walls with 2 neighbors. This cell would not be infected initially because it only shares 1 wall with someone that's infected. So we would see after 1 moment in time, these 2 cells would get infected. After another moment in time, we would get 2 more here, and then 2 more here, and then the infection stops. So the question first is, what's the easiest initial state that will ensure everyone is eventually infected? Initially, students tried to be clever, and I had to tell them to stop being clever, and eventually they said, infect everyone. And it's very easy to see that if everyone is infected, then everyone is infected. Now the problem is that this means we have to infect on the order of n squared squares, that's painful, out of n squared squares to ensure that everyone is infected. So that's 100%. So the question is, can we do better? So the first is, notice that the exponent of the number of squares on the n squared is 2. We have to infect n squared. We can try to lower that exponent, or we can try to lower the constant in front of n. So the first was to try to get a better constant than n squared. So one person suggested we infect everybody but the upper left corner. And that would require fewer cells, and we would now have n squared minus 1 cells, but it would still be 100% of the cells in the limit. And then someone suggested, well, let's use a checkerboard pattern. We often see checkerboards, chessboards, and if you infect every other cell, then it turns out that you will get everyone infected. So this would now allow us to do it with 50%, or 1/2 n squared. So it's a nice question, we didn't ask this initially, is there a way to do it with just 25% of n squared? Is there a way to infect 1 out of every 3 or 1 out of every 4 cells and still do it? So I'll leave that as something to ponder. Then the question was, can we do better than having something of size n squared? And the suggestion was to infect the main diagonal. And if we infect the main diagonal, we see the infection spreads out, and very quickly everyone gets infected. So then the next question was, what if we have n minus 1? Is it possible to do that? And we thought a little bit about this, and eventually we came back to one of the things we've been doing a lot in this class, is looking at lower cases. Looking at what if we have, instead of an n by n grid, what if we have a 1 by 1, 2 by 2, 3 by 3? And so we see if we have a 1 by 1 grid, well, we can't infect anyone, so there's no way the infection can spread. If we have a 2 by 2, we see that with a 2 by 2, we could infect 1, and then nothing else would be infected. For the 3 by 3, this is just like the tic-tac-toe problem. And for the tic-tac-toe problem, we saw that there are 3 opening moves up to symmetry, and then after that, there are only 5 responses to one, 5 responses to one, and 2 responses to the other. So there's 12 cases. It's not that bad to go through 12 cases. We can do 12 cases. It's not pleasant, but it gets harder as you go further and further. This next suggestion was to try to do this by induction, but by induction this is becoming painful. So we then went to looking at monovariants. So was it recording by this point? Had we switched, guys?
I think so.
Yeah.
I think so, yeah.
So I'll just say really fast, if we do it with monovariants, a monovariant is a quantity that only moves in one direction. So an invariant is something that's unchanged. If you rotate a triangle, if you translate a triangle, its area doesn't change. A monovariant, it either stays the same or goes down at every moment in time, or it stays the same and goes up at every moment in time. So here, if I have two cells that are infected, they would infect the one between. In terms of the perimeter, I now lose these two walls over here, and I maybe gain these two walls over here. I might not, depending on whether or not I have stuff up over here. And we want to do the simplest possible argument. I don't want to go through all these different cases, but sometimes you have no choice. So if a cell is going to be infected, it turns out there's only really a few possibilities. I could have east-west infected, north-south infected, 3 out of 4 infected, or 4 out of 4 infected. Alright, so we're going to stop here because from this point onward I think we've already done it. And we will sign off and move to the regular class in a moment.